What if I told you this isn't an expensive industrial actuator, but just a cheap motor controlled by code you can write using hardware that only costs about 30 euros. 3 months ago I knew nothing about field-oriented control. Just like you, I googled FOC tutorial but found nothing useful. That's why I'm creating this video series, so that people like you who want to implement an FOC on real hardware from scratch know how to do it and don't have to go through the struggle I had. My name is Salim and welcome to my video series How to FOC from Scratch. After watching this series, you will know how to design and implement your own FOC from scratch, allowing you to control your motor's position, speed and torque or current. But only if you watch all my videos. This series is split into several videos, where I will guide you step by step through the implementation while keeping everything as general as possible. I will be completely transparent and show you exactly how I did it and which hardware I used, so you can follow along step by step. Since this series is about practical implementation, I will assume you already understood how FOC works. If not, I've linked some great videos in the description. Before we start coding, we need the right hardware. And choosing the right hardware isn't easy. It's an iterative process where you often have to go back and forth to find the right combination of components. A good strategy is to pick one key component like the microcontroller and then choose the other components to match it. Here is what I'm using. The brain for my FOC is the Teensy 4.0 microcontroller. The muscle of my FOC is the GM2804 BLDC. To drive the BLDC, I'm using the DRV8313 motor driver, which is used on the SimpleFog Mini V1 board. Since this isn't a sensorless FOC, I'm using the ENA226 current sensor to measure the phase currents. Right now I am working on my own 2-channel high-speed, ultra-precise current sensor based on the ENA241. If you're interested, let me know in the comments and I'll make a video about it. Lastly, I use the MT6835 magnetic encoder to measure the absolute mechanical angle of the motor shaft. Alternatively, you could use the MT6701, which is cheaper but less accurate. Note, I designed those PCBs myself and got them from PCBWay. If you need high quality PCBs, 3D prints, CNC parts or even sheet metal fabrication, PCBWay is your go-to. They offer fast turnaround times, affordable prices, and their online quoting system makes ordering super easy. Whether you're a hobbyist or a pro, PCBWay helps bring your ideas to life. Check them out using the link in my description below. Big thanks to PCBWay for providing these PCBs and for sponsoring this video. If you want, I can go into more detail about choosing the right hardware in a separate video. Just let me know in the comments. Now that we know our hardware, we'll start by reading and calibrating the sensors, one by one until everything works perfectly. As you know, to control something, we usually first need to measure it. For position control, we need the incremental mechanical angle of the motor shaft. For speed control, we need the mechanical angular velocity of the motor shaft. And for the torque or current control, we need the phase currents and the absolute electrical angle. That may sound like a lot, but the good news is that almost all of these measurements, except the phase currents, can be derived from just one sensor, the magnetic encoder, which measures the absolute mechanical angle of the motor shaft. To make this sensor work, you need a diametrically magnetized magnet, which means the poles are on the opposite sides, not on the top and bottom. The magnet must be precisely placed on the motor shaft with the sensor mounted above it. The sensor detects changes in the magnetic field orientation and converts them into an angle reading. Make sure to check the datasheet for the correct placement. If you did everything right, this is how it should look like. It's very easy to read this sensor data, especially since there are many libraries. Now let's talk about the incremental mechanical angle data, which is needed for our position control and how to derive it. Let's say you rotate your motor past 360 degrees. We don't want the reading to jump back to 0 degrees, right? To fix this, we introduce a counter variable that tracks jumps. If the angle jumps from 360 degrees to 0 degrees, we increase the counter by 1. And if the angle jumps from 0 degrees to 360 degrees, we decrease it again by 1. But how do we detect a jump and its direction? We first calculate the difference of the current absolute mechanical angle value and the previous value. If the difference is smaller than minus 180 degrees, it's a positive direction jump. because we jump from 360 degrees to 0 degrees. Therefore, we increase the counter variable by 1. If the difference is greater than 180 degrees, it's a negative direction jump, because we jump from 0 degrees to 360 degrees, and therefore we decrease the counter variable by 1. The plus minus 180 degrees threshold ensures accurate detection even at high motor speeds. Now we can calculate the incremental mechanical angle using this formula. The incremental mechanical angle is equal to our absolute mechanical angle plus our counter variable times 360 degrees minus our initial absolute mechanical angle value. When restarting the system, the counter variable resets to 0, causing the incremental mechanical angle to match the absolute mechanical angle. To ensure the incremental mechanical angle starts at 0, we store the initial absolute mechanical angle at startup and subtract it. During this initialization, we disable jump detection to keep the counter variable at 0. If you have done everything right, this is how it should look like. Make sure to measure in SI units, not in degrees. I only use degrees for explanation purposes, but the actual data should be read in SI units. Wow, that was hard, but we did it. Thank you for watching so far. If you are enjoying this video, please consider supporting me by subscribing, liking, or leaving a comment. Now that we have the incremental mechanical angle, we can use it to calculate the mechanical angular velocity. The mechanical angular velocity is simply the difference between the last two angle readings divided by the step time. Make sure to measure in SI units, not in degrees per second. Now let's talk about the electrical angle. The electrical angle equals the sum of the absolute mechanical angle and the absolute mechanical offset multiplied by the number of pole pairs. The modulo function simply ensures that we stay within the range of 0 to 2 pi or 360 degrees. As you can see, to calculate the electrical angle, we need to determine the number of pole pairs and the electrical offset. Most of the time you can find the motor specifications, such as the number of pole pairs, in the datasheet. But what if you can't find one? No problem, here's a simple trick to determine the number of pole pairs yourself. Ground two motor phases and connect the third one to your power supply. Slowly increase the voltage until the rotor locks in place. Slowly! If you are unsure about the motor's maximum voltage and current ratings, use a low voltage and current and pray that nothing happens. Gently rotate the shaft one full turn and count the distinct lock positions you feel. That's your pole pair count. 1, 2, 3, 4, 5, 6, 7. In the next video, we will cover how to calculate the electrical angle offset, generate PWM signals to run your motor, and finally measure the phase currents. These are the last steps before we will dive into the control algorithm in the third video. Don't forget to subscribe so you don't miss it. Thank you for watching and see you next time.